Hello friends, welcome to my YouTube channel, and today we are going to study about the waves and sound part 3. In the previous videos of waves and sound, we have started with the basics of the waves, then we have seen the superposition of waves and the stationary waves and interference of waves we have seen. Now today we are going to study about the bits and Doppler's effect. So let's start the video. So first we will see about the bits. This is one of the important topic in the waves. So first we will see how the bits are formed. So bits. So when two interfering waves, two interfering waves having slightly different frequency, slightly different frequency, the resultant disturbance at any point due to the superposition of these waves periodically fluctuates, causing waxing and waning in the resultant intensity. The waxing and waning in the resultant intensity in the resultant intensity of the two superposed waves of slightly different frequencies are known as bits. Are known as bits. So what is basically bit? So we have seen the interference of the waves also when the waves have equal frequency and nearly equal amplitude. That is known as interference, superposition of waves basically. Now here also we are going to study about the superposition of waves, two different waves, but their frequency will be different. And when the frequency will be different, and when they will superimposed on each other, the resultant displacement or the resultant disturbance at any point due to this superposition, it will fluctuate periodically, and due to this fluctuation there will be waxing and waning in the resultant intensity, and this waxing and waning that is produced in the resultant intensity of two superposed waves is basically known as bits. So now we will see the mathematical equation. So these are the equations of two waves. Suppose we have two sources here. So let me take let the two waves are let the two waves be, I'm just letting the displacement of these two waves, or the particles, oscillation of particles of these two waves, y1 is equal to a sine of omega t plus kx. In the same direction I'm taking, or kx minus omega t we can take. So I'm taking omega is equal to 2 pi, so 2 pi f1 into t minus kx, and the equation of displacement of the oscillation of second particles, or particles of second wave, y2 is equal to a sine, their amplitude is same, 2 pi, frequency is different, f2 into t minus kx. These two are the equation of the waves. Now when they will superimpose at any point P, then the resultant displacement y, according to superposition principle, it will be equal to y1 plus y2. So by the principle of superposition, we can say that by the principle of superposition, we can say that y equals to y1 plus y2. The resultant displacement is equal to the vector sum of displacement of the waves. Y is equal to y1 plus y2. If we can write down this equation, or if we just analyze this equation at x is equal to 0, then this equation will reduce to this form. So I can write down y1 equals to a into sine of 2 into pi into f1 into t. If we are interested only in if we are interested only in analyzing the frequency, what will be the effect on the resultant displacement due to the frequency, this difference in the frequency only, then I'm writing 2 pi f1 into t, and similarly this second equation can be written as y2 is equal to a sine of 2 pi f2 into t. In terms of frequency, here I am taking x is equal to 0. By taking x is equal to 0, these two equations will be reduced to this form. y1 is equal to a sine 2 pi f1t, and y2 will be equal to a sine 2 pi f2t. Now according to principle of superposition, now we can solve this equation. So y will be equal to y1, just replace the value of y1, equals to a sine of 2 pi f1 into t plus y2 is equal to a sine 2 pi f2 into t. Now after solving this equation, since a is common to both these terms, so we can write down y equals to a into sine of 2 pi f1 into t plus sine of 2 pi f2 into t. So this equation is of the form sin C plus sin D. I am taking this term as C. Suppose this term is C and this term is D. Then this is of the form of sin C plus sin D. So we are going to use this equation sin C plus sin D. It will be equal to 2 into cos C minus D by 2 into sin C plus D by 2. I am going to use this formula in order to reduce this expression. So this equation will be reduced to y equals to a, and when you will reduce this expression inside this bracket, this will be equal to 2 into cos of C minus D by 2. So 2 pi f1 minus f1t minus 2 pi f2t divided by 2 into sin C plus D by 2, sin C is equal to 2 pi f1t plus 2 pi f2t divided by 2. Now this equation will be reduced to this equation. Now we can solve this equation. So it will be equal to y equals to a. It will become basically 2a outside, and 2 cancel, pi also cancel. So basically we can write down 2 pi f1 minus f2. We can write down cos of 2 pi is common, 2 pi t is common. So basically we can write down 2 pi f1 minus f2 into t divided by 2 into sine of 2 pi f1 plus f2 into t divided by 2. This will be your expression basically. Here we can write down this. This is our basic equation. Okay. So when we will analyze this equation, here I have taken f1 is greater than f2. Here f1 is greater than f2. Okay, and we have written this equation. Now we are going to define one term that is known as the time for one bit. What will be the time for one bit? So clearly you can see here from this equation, uh, we have this equation y is equal to 2a cos 2 pi f1 minus f2 into t divided by 2 into sine of 2 pi f1 plus f2 divided by 2 into t. Now clearly we can define what is the time for one bit. So the time for one bit is the time between consecutive maxima or minima. So when the first maxima will occur, because the standard equation of wave is y is equal to a sine omega t or sine kx minus omega t. So basically this part, if we can rearrange this equation, we can rearrange this equation like this also. So we can write down y equals to 2a into cos of 2 pi into f1 minus f2 into t divided by 2 into sine of 2 pi f1 plus f2 into t divided by 2. So basically this part, if you will look here, this part is representing the amplitude of the wave. Okay, amplitude. This part is representing the amplitude basically. So we can write down basically amplitude A is equal to the resultant amplitude A is equal to resultant, it is equal to 2a into cos of 2 pi into f1 minus f2 into t divided by 2. And clearly you can see that this amplitude is a function of time. With the time this amplitude will change. Obviously it will get its maximum value and its minimum value. Now what will be the time duration between these two values? We can calculate. Now the new term is here. What will be the time for one bit? So the time for one bit, the time for one bit is the time between is the time between consecutive maxima or minima. The time duration between two consecutive maxima or minima is nothing but it is the time for one bit or minima. Now let me calculate, or let us calculate what will be the time duration for maxima. So first we are going to calculate what will be the first maxima. So the first maxima will occur when this cos will take its maximum value. First maxima will occur when this cos value, it will be plus 1, cos of 2 pi f1 minus f2 into t divided by 2, it will be equal to 1 plus 1. Okay, because the maximum value of cosine function is 1. Now after solving this equation we can write down, we are getting maximum value of cos at cos 0. So cos of 2 pi f1 minus f2 into t divided by 2, it will be equal to cos of 0, because cos of 0 is equal to 1. Now if you will analyze the angle, then we can say that 2 pi f1 minus f2 into t divided by 2 equals to 0, or here we can calculate this time. So t will be equal to 0. So first maxima will occur at t is equal to 0. Now second maxima we can calculate, and second maxima would occur in negative direction basically, and we can calculate time for second maxima. Second maxima will occur when this cos value, cos of 2 pi f1 minus f2, maximum amplitude I'm talking about, into t divided by 2, it is equal to minus 1. Here the minimum value of cos function is minus 1, but when we take the modulus only, we are talking about the magnitude only, then it will be equal to minus 1, and this minus 1 we are getting at pi. Cos pi is equal to minus 1. So if you will analyze this, then we can write down cos of 2 pi into f1 minus f2 into t divided by 2, it is equal to cos of pi. And if you will analyze this equation, then we can write down 2 pi into f1 minus f2 into t divided by 2, it is equal to pi, and from here we can calculate the value of time. So basically t will be equal to how much? T will be equal to 2 cancel out, pi cancel out, it will be equal to 1 upon f1 minus f2. So this is the time for second maximum. Now we are going to calculate what will be the time duration between two successive maximum, this two value. Suppose I'm writing this equation as equation A, and this is your equation B. Now what will be the time duration between these two consecutive maxima, first maxima and second maxima? So we can easily calculate, and that time duration is nothing but it is the time for one bit. So now we are going to calculate time for one bit. So now we can calculate time for one bit. So time for one bit, it is nothing but it is the time interval between two consecutive maxima or minima. Here I have taken maxima condition. So time duration, the final second maxima, it is 1 upon f1 minus f2, and first maxima it is obtained at t is equal to 0. So this value it will be equal to 1 upon f1 minus f2. So this is the time duration for one bit. Now we are going to define the bit frequency. New term is there, bit frequency. What is bit frequency? So the definition of bit frequency is the number of bits, the number of bits, the number of bits in 1 second, in 1 second. So we can easily define this, or reciprocal of time period is basically frequency. So time for one bit we have calculated, so it will be equal to 1 upon 1 by f1 minus f2. Okay, and it will be equal to f1 minus f2. If f1 is greater, then we can directly take f1 minus f2. If f1 is less than f2, then we need to take the modulus value. So f1 minus f2 means difference of frequency of two waves. It will give you the bit frequency. Okay, so now we are going to solve one problem related to this, but here we can study about the graph also. How we can study about the graph? So this is the pattern basically. Let me draw the pattern. We can easily plot the graph in order to study the. Let me draw the graph first. For first wave, I'm writing y1 is equal to a sin omega t minus kx. This is the shape basically, suppose. This is for y1, suppose. y2 also we can write down. This will be the shapes. Sine wave will be there. Suppose this is y2. Okay, this is your y2. And when they superimpose, this will be equal to y1 plus y2. This will be your y1 plus y2. We can easily plot like this. Suppose by third wave I am representing. Let me take with the black. Somewhere it will be waxing, somewhere it will be waning. Like this way we can take, no problem at all. Somewhere it will be waxing, somewhere it will be waning, and due to this resultant displacement, we can get a graph like this. You will get. Okay, let me plot the graph. The green. So this shape of graph basically you will get. So this is due to the superposition. So this is the final graph you will get in case of bit formation. Now we are going to we are going to solve one numerical here, very small numerical we will calculate. So let me take one problem here. So the question is, two tuning forks, two tuning forks P and Q, P and Q, when set vibrating, when set vibrating, give 4 beats per second, 4 beats per second. If a prong of the fork P is filed, if the prong of of the fork P is filed, the bits are reduced to 2 per second, 2 per second. Determine the frequency of P. Determine the frequency of P, means frequency of the wave produced by the tuning fork P. Determine the frequency of P. If that of Q is, if that of Q is 250 Hertz. So this is the problem. So we can easily solve this problem using the concept of this bit frequency. Let me solve this problem for you now. So before solving this problem, let us understand what is tuning fork. Okay, so this is basically the shape of the tuning fork. This shape of the tuning fork you will get here. The lab, in the physics lab, you can see this is the shape of the tuning fork. This is U shape. This is the handle. These are known as prongs. Prong, prongs. These two ends are known as prongs. Now, when they are heated or when they are just striking over a wooden board or anything, so sound, they will start vibrating and they will produce the sound of some frequency. So we have this is basically the shape of the tuning fork. So basically we have two tuning forks P and Q, and they are producing sound waves, and the bit frequency of this tuning forks P and Q is basically 4 beats per second. So there are 4 bits between P and Q, therefore the possible frequency of P are 246 or 254. Why? Suppose let me take this. Suppose F1 is equal to, let me the dark color here. F1 is equal to frequency of the wave produced by P, tuning fork P, and F2 is equal to frequency of the wave produced by Q. Now we know the bit frequency. The bit frequency is nothing but it is the modulus F1 minus F2, because we don't know which has got the maximum value. So F1 minus F2, the initial condition is given. This is bit frequency, it is equal to 4. So F1 minus F2, it can be written as plus or minus. So first I'm writing plus if F1 is greater than F2. If F1 is greater than, then this value F1 minus F2, it will be equal to 4 if F1 is greater than F2. Otherwise, this value, it will be negative. It will become F2 minus F1, or we can write down minus of F1 minus F2, it is equal to 4. Okay, it will become F2 minus F1 if F2 is greater than F1. These two equations, and from here, because we know the value of F2, this value is given. What is the value of this? It is given 250 Hertz. So now we can put the value of F2, then F1 will become 4 plus F2 from this equation. Okay, and from here we can calculate the frequency F1. F1, it will be equal to 4 plus 250, that is equal to 254 Hertz. Now if you will take this second equation, then we can write down F2 minus F1, it is equal to 4, and from here we can calculate the value of F1. F1 will be equal to F2 minus 4, that is equal to 250 minus 4, that is equal to 246. So basically the possible values of this F1 is equal to either 254 Hertz or 246 Hertz. Now moving to the next condition. The next condition is given when the prong of this fork P is filed. Filed means when this thickness is reduced. When there is filing of this prong, these are known as prongs, the bit frequency reduces. Now then on filing, its frequency will be greater than 254. The bits between P and Q will be more than 4, but it is given that the bits are reduced to 2. Therefore, 254 is not possible. Therefore, the required frequency must be 246 Hz. Why? Now, the condition is given when we are filing, this prong of this tuning fork P, because now we have obtained basically two frequencies, 254 and 246, but only one frequency will be there. of the wave that is produced by the prong of P. Either it will be 254 or 246. Okay, so now we will see which value will be applicable here. So when the prong P is filed, its frequency becomes greater than the original frequency. When we will file any, when we are uh, decreasing the thickness of this prong, then what will happen? Its frequency will increase. Okay, so if we assume that original frequency of P is 254, then on filing its frequency, when we will file its frequency, that will be greater than 254, and the bits between P and Q will be more than 4, which is not possible. So we can say that this frequency 254 is not possible, therefore the required frequency must be 246. Now look, again I am explaining. Just we have obtained two values of f1. So these two values of f1 are, so we have obtained the value of f1, that is the frequency 254 and 246, but only one value will be there. Now in the problem it is given when we are filing, when we are filing the prong of P, the prongs of P, the frequency f1 will increase, because on filing the length will be reduced and it will produce the waves of sharper, sharper intensity, we can say, means frequency will increase, f1 will be more. And if f1 will be more than 254, suppose f1 is more than 254, then the difference of f1 and f1 is equal to 54 and f2 is more than 254 and f2 is equal to 50. So the difference will be more than 4, but the difference is given only 4. Okay, so this frequency is, when we are filing the prong of P, the frequency f will be more, and this difference f1 minus f2, okay, it will be greater than 4, which is not possible. So we can say that the frequency f1 will be equal to how much? It will be equal to 246. Okay, so this is the value of frequency that is produced by the prong of, or the prong P. Now next topic is Doppler's effect. So the next topic is Doppler's effect. Doppler's effect. First we will see the what is Doppler's effect. So the apparent shift in frequency of the wave motion of the wave motion when the source of sound, when the source of sound or light moves with respect to the observer is called Doppler's effect, is called Doppler effect. Doppler effect. So basically when there will be a relative motion between the source of sound or wave and the observer, the frequency that will be heard by the observer, that will be different from the actual frequency, and this effect is known as Doppler's effect. So now we are going to calculate the apparent frequency, the frequency that is received by the observer in the different situations. So now we are going to calculate calculation of Doppler's frequency or apparent frequency. So now calculation of apparent frequency, apparent frequency. So let V is equal to velocity of sound in air, and Vs is equal to velocity of source of sound, velocity of source of sound. Suppose source of sound is also moving and its velocity is equal to Vs. V naught is equal to velocity of the observer. If the observer is moving, velocity of the observer, and F equals to frequency of the source. F equals to frequency of the source. Now we can easily calculate the apparent frequency in different situations. The first situation I'm just creating here is when the source is moving towards a stationary observer. Suppose observer is stationary and a source of sound or source of wave is approaching towards the observer, then what will be the frequency heard by the stationary observer? So that will be your apparent frequency. Now we are going to calculate the first case. The first case is when the source is moving towards the observer. So the first case is source is moving towards stationary observer. Stationary observer. The observer is stationary and the source of sound or the source of wave is moving towards the stationary observer. So just let me calculate this. So now suppose this is the position of the source. This is the position of the source. Here one source of wave or source of sound is there, and here this is the position of the observer. Now this source of sound is transmitting the sound waves or the waves, simply we can say. This is your observer O. Now this source of sound, it is transmitting the waves in this direction, like this we can take. Okay, and it is approaching towards the observer. Okay, so what will be the distance traveled when suppose it is reaching to the observer? The wave is emitting from this source. This S is the source. Okay, and O is the observer. Now this source is emitting the waves and it is reaching to the observer. So what will be the distance covered in time t? If v is the speed of the wave, sound wave that is emitting from this source S, then what will be the distance traveled? The distance is equal to speed into time. V into time we have taken in 1 second. So V into 1, it will be equal to 1. So this will be the, basically this will be your distance between this source and observer. Okay, this V we can take and this will be equal to V. Okay, but since this source is also moving, so after some time this source is moving with the speed Vs. So after time t, the position of the source will change and this will be the new position. Suppose after some time or after 1 second, this is the new position. Now source is here. Now observer is stationary, so observer will remain its, or it will remain at its original position. And again this source of sound is continuously emitting the waves, sound waves or simply waves or light waves. Okay, and it is reaching to the observer. So what will be the distance traveled by the source in 1 second? Okay, the speed of the source is suppose Vs, then the distance traveled by this source in 1 second, it will be equal to Vs into 1, and this will be your distance here. This will be the distance traveled by the source in 1 second. This will be the distance, and since it is moving towards the observer, so this distance now this distance I'm taking Vs. Okay, the distance traveled by this source in 1 second, it will be equal to speed into time, that is Vs into 1, that is equal to Vs. And when I've taken the initial condition, if the speed of the wave that is emitted from source S is V, then in 1 second the distance travel will be equal to V into T, sorry, V into 1, and it will be equal to V. In 1 second, per second we are calculating this basically. So now the waves will be occupied in this space, this distance only after 1 second. This will be the space occupied by these waves. Okay, this will be the space occupied. You can see it here. This distance. Now this distance will remain as V minus Vs. The initial position or the initial distance between source and observer is V. Now this distance, it will become V minus Vs after 1 second. So we can write down this distance will be equal to V minus Vs after 1 second. So if the source were stationary initially and f number of waves are sent out in 1 second, f number of waves or n number of waves you can say in 1 second, then the observer O would occupy a distance V and the wavelength would be V by F. In this case, in first case, I'm taking, let me take what will be the wavelength. Okay, the relationship between wavelength and frequency. Here I'm taking wavelength, initial condition. Wavelength is equal to lambda, and number of waves per second I'm taking F. Frequency, so number of oscillations per second we write as F. Then and a speed also, a speed of the wave we have taken a speed of the wave. Okay, it is equal to V. Then what will be the frequency or what will be the wavelength? Wavelength, frequency into wavelength. Frequency into wavelength is equal to speed of light. So from here we can calculate for initial condition, lambda will be equal to V by F, where V is the speed of the sound or speed of the wave and F is the number of waves in 1 second. So this will be your original wavelength when the source and observer both are stationary. But since source is moving, now this V minus Vs, now within this distance the waves will occupy. So if S is moving with velocity Vs towards O, then F waves sent out occupy a distance V minus Vs only, because S has moved a distance Vs towards O in 1 second. So the apparent wavelength will change. Now what is the apparent wavelength now? The new wavelength. Okay, so now apparent wavelength, in this case we can calculate apparent wavelength. So apparent wavelength, it will be equal to the distance. The initial distance was V. Now distance is reduced to V minus Vs, and number of waves occupying the space is, sorry, the number of waves sent out is now F is only there. Okay, in per second the number of waves sent out is F, but now these waves are occupying the space V minus Vs only, or the distance V minus Vs only. So this will be the new apparent wavelength lambda dash. It will be equal to V minus Vs by F. So if the wavelength is changing, then we can calculate the apparent frequency also. So now we can write down now apparent frequency, apparent frequency. Suppose I'm writing apparent frequency by F dash, then we can write down F dash, it will be equal to speed of wave, it cannot change, so we can write down V, and apparent wavelength, it is equal to lambda dash. So now we can put the value. So this F dash will become V, and put the value of lambda dash. Lambda dash is equal to V minus Vs by F. And if we will solve this equation, we will get F dash equals to F will come in the numerator, so F into V by V minus Vs. So this will be your new formula here that we have obtained. It's very simple now to analyze. Let me calculate this for you. So this is the new frequency here, okay, or apparent frequency, where F dash is the apparent frequency, F is the original frequency, V is the speed of wave, and Vs is the speed of the source towards the observer. Okay, so this first case I have calculated. Now second case we can take now. The second case is when source is moving away from the observer. So this is the second case now. Now second case we are going to see here. The second case is number 2. Then we will generalize this. Source moves, means source of sound or source of wave is moving. Source moves away from stationary observer. Stationary observer. Okay, observer is still stationary, but now in this case the source is moving away. Let me take this here. We have one source of sound here. We can take, this is your source S, and this is your observer. Initially this source is emitting the light waves or sound waves, and this is reaching towards the observer. You can see it there. This is the direction in which the waves are sent. The waves are sent with the speed v. So how much distance they will occupy in 1 second? It will be equal to v into 1. That will be equal to v only. So here we can calculate. We can easily calculate. Okay. So here we can calculate this distance. Suppose in 1 second f number of waves are sent out from this source S and it is reaching at point O. Then how much distance they will travel? When both source and observer are stationary, this distance will be basically equal to v into 1. V into 1, and that will be equal to v simply. So we can say f number of waves, okay, f number of waves are sent out from S, source S, and these waves reaching at O, means at observer O, in 1 second. Per second we are going to calculate. Okay, so this is the initial case. Now f number of waves are sent out from the source S and reaching at observer O in 1 second. So how much distance they will occupy? So I can say f number of waves are occupying a distance of v in 1 second. Okay, initial case when both source and observer are in a stationary. So we can say v is equal to the distance occupied by f number of waves. F number of waves will be, so in this case the wavelength lambda will be equal to v by f. In this particular case we can calculate lambda is equal to v by f. But since this source is moving away from this observer, so after 1 second, suppose this is the distance traveled by the source. In 1 second it is moving away now. So in 1 second it will move a distance that is equal to Vs. Distance traveled by this source towards the left, it will be equal to Vs into 1. That will be equal to Vs. And now this total distance now it will become V plus Vs. V plus Vs, V plus Vs, and this will be your new position of the observer. Observer will remain at the same position, and this will be the new position of the source. Now this source is moving away. Okay, this source is moving towards the left. So now we can say that the total effective distance, it will become now V plus Vs after 1 second. Okay, so what will be the apparent frequency in this case? Now we can write down now apparent wavelength. Apparent wavelength, suppose I'm writing for this case is lambda dash, then it will be equal to how much? It will be equal to V plus Vs, the total number of waves that they are occupying a distance of V plus Vs after 1 second, divided by frequency. The frequency is f, means number of waves that is reaching at O per second, f. Now, so apparent frequency, so apparent frequency f dash, it will become V by lambda dash, and we can write down V by lambda dash can be replaced with V plus Vs divided by f. So this f dash will be equal to f into V divided by Vs. So this is the apparent frequency and the frequency of the original source of sound. Vf dash is equal to f into V divided by V plus Vs. Now similar explanation can be given. In the similar way, we can derive the apparent frequency for other two cases. Now the third case is, now observer is moving towards the stationary source. Okay. Now the third case is observer moving towards a stationary source. So suppose this is source of sound, S is the source of sound, and it is emitting the sound wave or light waves, and it is reaching to the observer. Okay, this is your observer in 1 second. So in 1 second it will occupy a distance. Suppose this source of sound, it is has got the speed v, then it will occupy this distance in 1 second. V into 1, that will be equal to v. V into 1, that will be equal to v. So for this case we can calculate the apparent wavelength and frequency. The actual wavelength lambda will be equal to v by f. This is your equation number 1. But the second case is, now this here is the source. Source is just emitting the same number of waves, f number of waves, but this observer, now it is moving. This observer is moving. So this is the new position of the observer. This is the new position of the observer. Okay. So how much distance will be traveled by this observer? Suppose I'm writing in 1 second, it will be equal to V naught. It will be equal to V naught. So this is the case now. So what will be the apparent frequency in this case? The apparent frequency in this case, it will be equal to velocity of sound relative to the observer O. Now we can see it there. Both are moving opposite to each other. Here you can see it there. This is the direction in which the sound is traveling. V. Okay. And this V naught is the speed of the uh, observer, which is moving towards the stationary source. Now in this case, we can easily calculate what will be the new frequency. Basically, the new wavelength, the new speed, it will be equal to V plus V naught it will be. Okay, because we are dealing with the speed of the sound here, or speed of the wave and the speed of the observer. Now here in this case, the apparent frequency the apparent frequency f dash, it will be equal to velocity of sound relative to observer O divided by wavelength of wave reaching O divided by wavelength of wave reaching O. Okay, frequency is equal to basically speed divided by wavelength. So now f dash, it will become velocity of sound relative to O. If we are going to calculate the relative velocity, they are opposite to each other. So relative velocity, it will become v plus v naught. So it will become v plus v naught divided by the wavelength. The wavelength is lambda, and lambda can be written as v by f. So f dash will be equal to v plus v naught divided by lambda. Lambda can be replaced with v by f, and we can write down, basically this equation can be modified as f dash is equals to f into v plus v naught divided by v. So this is the relationship between apparent frequency and actual frequency. Okay, this is the final result that we have obtained. Now the last case we can take is, now the source is moving, the observer is moving away from the stationary source. Observer is moving away from the stationary source. If the observer is moving away from the stationary source, okay, and suppose they are in the same direction, then apparent frequency f dash can be written as velocity of sound relative to observer. It will be minus sign, that will be equal to v minus v naught divided by wavelength. Wavelength is equal to v by f. So this equation will be modified as f dash will be equal to f into v minus v naught divided by v. This is the apparent frequency f dash, and f is the actual frequency, v is the speed of wave, and v naught is the speed of the observer. So this is the case. These are the four cases. Now we can combine all these cases. If both are moving, okay, if both move away from each other, the next case also we can analyze. Individually we have analyzed. Now suppose the next case we can also analyze. Source and observer moves towards each other. The next case is source and observer moves towards each other. So we can combine the two cases when observer is moving towards the source and source is moving towards the observer. Then the apparent frequency f dash, it will be equal to f, observer is moving towards the source, then it will become v plus v naught, relative velocity of sound with respect to observer, divided by v minus vs. Okay, this will be equal to v minus vs. Now if they are moving away, source and observer moving away from each other. If they are moving away from each other, then the apparent frequency f dash, it will be equal to f into v minus, it will become v naught divided by v plus vs. So these are the cases, 6 cases of the apparent frequency when the source and And when source and observer are in relative motion with respect to each other, what will be the apparent frequency and actual frequency? The whole can be summarized in this form. Okay, plus minus sign you can take according to the cases. This will be the final result basically. This will be your final result. Okay, f dash, it will be equal to f into v plus minus v naught we can take observer. The top, always remember, it will be observer divided by v plus minus vs. Okay, plus minus vs we can take. Okay, when both are stationary, means observer is stationary, then v naught will be equal to 0. And when case number 1 we can take, and when a source is also stationary, it will be equal to 0. Then this equation will be reduced at f dash will be equal to f into v plus minus 0 divided by v plus minus 0, and it will be equal to simply f, means apparent frequency is equal to actual frequency. Apparent frequency equals to actual frequency. Okay, number 1. Number 2 we can analyze. This is the actual formula. Number 2 we can analyze. Okay, plus sign and negative sign we can choose accordingly. So when observer is stationary, means observer stationary means velocity observer it will be equal to 0, and source, okay, source is moving vs. If source is moving towards the observer, okay, if source is uh, moving towards the observer, it will be equal to minus sign, then vs will become minus of vs. Okay, source is moving towards the observer, and accordingly we can modify this equation. Then f dash will become f into v divided by v minus vs. If the source is moving towards the observer, the frequency will increase. Sorry, f dash, yes, v minus vs. And in this way we can analyze all the cases. Third, when observer is a stationary, means v naught will be equal to 0, and source is moving away from the observer, then vs will be positive sign. Okay, towards, you can say, towards the observer, and this is away from observer. And in this case we can calculate f dash will be equal to f v plus minus 0 v divided by v plus vs it will become. In this way we can analyze all the cases also. Now if we'll consider the wind effect, okay, in the sound, then we can take another term also, wind effect. Okay, so if wind is blowing along the direction of uh, the wave emitted by the source, then the actual speed of the wave it will become v plus vw. Okay, taking into account the wind effect, it is the now velocity of wave. This will be the new velocity of wave if wind is blowing, okay, blowing in the same direction of wave propagation. Okay, otherwise this value will be v minus vw, velocity of wave. Okay, if the wind is blowing opposite direction, in the opposite direction of wave propagation. So these are the 5 situations in these cases. Now let us take one numerical to understand the concept of this Doppler's effect. So the problem is, a source of A sound of frequency 256 Hz, a source of sound of frequency 256 Hz is moving towards a wall with a with velocity of 5 meter per second. How many bits how many bits per second will be heard by an observer standing in such a position standing in such a position that the source S is between observer O between observer O and the wall okay. Now speed of wave it is given, or speed of sound it is given, it is equal to 330 meter per second. Now let's analyze this problem, then we will solve this problem. First we will read this question again. So a source of sound of frequency 256 Hz, its actual frequency is given. Okay, so actual frequency is given, it is equal to 256 Hz. Okay, one more thing is given, the speed of the sound it is given 330 meter per second, is moving towards a wall with a velocity of 5 meter per second. The speed of source is also given. Okay, the speed of source of sound it is also given 5 meter per second, and it is moving towards a stationary wall. How many beats per second will be heard by an observer standing in such a position that source S is between observer O and the wall? Okay, the source S, okay, in such a position that the source S is between observer O and the wall. So first let me draw the diagram. Okay, from diagram we can analyze this problem, then we will solve this problem. Okay, so now this is the case here. Let me draw one line first. This is the line, and this is your wall. Let me take the wall also. Okay, this is your wall. This is your wall. Okay, and now in the problem it is given how many beats per second will be heard by an observer standing in such a position that the source S is between observer O and the wall. So this is wall, and suppose I am taking this is your observer O. Okay, and this is your source S. Now what is bit frequency? Bit frequency, just I have explained earlier. The bit frequency frequency is equal to f1 minus f2 modulus sign. Okay, so frequency of sound that is directly heard we can easily calculate. This is the case. This is the formula we can use. Okay, because observer is a stationary, it is not moving, but source is moving towards the wall. This is the direction in which the source is moving. So the first case we can calculate frequency of sound directly heard means the source is moving and this source is emitting the sound wave and it is reaching to the observer. Then in this case we can apply the Doppler's formula. In this case I am taking this frequency as f1. Okay, f dash we can take. So f dash is nothing, f dash is equal to f naught. Since source is moving away from the stationary observer is a stationary, so I can write down v divided by v and minus of vs. Since it is moving towards the observer, sorry, it is moving towards the observer, so it will be plus sign, so away from the observer now, so it will be equal to plus of vs. F naught is given, it is equal to 256, v is given 330 divided by 330 plus 5. So when we will calculate this, the value will come out to be 252.2 hertz. So basically the frequency will reduce if the source is moving away from the observer. Now the second frequency that will be heard by the observer, it will come after the reflection from the wall. Okay, you can see it there. From here the source, the wave is emitted and after reflection we will get the second frequency. Okay, so this frequency also we can calculate. Now here you can see this this source is now it is moving, this wave is moving towards this stationary observer. So next case we can calculate frequency received by the wall, received by the wall. For this wall frequency we can calculate. So for this wall we can calculate this frequency is, now suppose I'm writing uh, f dash, I'm writing this frequency is f1. Okay, and f double dash we can calculate, it will be equal to f naught. Now since if wall is taken as observer, then it is moving towards the observer, then this will become v divided by v minus vs. So f naught is given 256 multiplied with 330 into 330 minus divided by 330 minus 5. When we will calculate, this frequency will be basically equal to 259.9 hertz. Okay, and this frequency I am taking f2. Since f2 is greater than f1, so now we can calculate beat frequency. So beat frequency, it will be equal to mod of f1 minus f2. So now when you will calculate, you will get 7.7 hertz. So that's all from this discussion. We have seen in today's video, we have seen about the beat frequency and Doppler's effect. Thank you everyone for watching.